All right, guys, welcome back again to another random banger. All right, at least that's what my friend said in the comments. All right, so what we're going to be doing here is to find the derivative of the inverse trigonometric functions. And before I start, let me just write the inverse trigonometric functions on this side. I'm going to label them at f at x. We're going to look at sine inverse of x, cosine inverse of x, tangent inverse of x, cotangent inverse of x, secant inverse of x, and cosecant, that's a C, inverse of x. All right, and I wrote them in this order because while it may seem that this video will be long, it won't, because when we find the derivative of sine inverse of x, cos inverse of x is just going to be the negative of that. And I'm going to explain why that is before jumping into the derivative with you guys. So let's go. And let's put f prime of x on this side. So that we can follow along. As soon as we get to the derivative, we write that on the other side. Okay, so before we start, let me just show you why cosine inverse of x will just be the negative of the sine inverse of x when we take the derivative. And we're going to start with a triangle. Let's draw a nice triangle right here. All right, and it's a right angled triangle that we're going to be using. Now, let's just say let sine x equals to y. Just saying, if sine of x is equal to y, from the trigonometric function, we know that sine alpha is equal to the opposite over the hypotenuse, right? Yeah, we would have learned that in high school. Now, if alpha here is x and the opposite is y, because we could represent this y as y over 1. Yeah, that's still y, right? So it means that the opposite side is y and the hypotenuse is 1. So if we take this angle right here to be x, then the opposite side, right, would be equal to y, because it's the opposite over the hypotenuse, right? And the hypotenuse, which is always the sine side, right here, 1. And we can find this side right here using the Pythagoras' theorem if we want, but not really necessary at this time. Another thing that we need to note is that within a triangle, that's a triangle sum theorem, all these angles right here, this angle, and this angle sums to a total of 180. But if we already know that this angle here is 90 degrees, then it means that this angle here plus this angle here should sum to 90 degrees. And we're not going to be using the degree measurement. I'm going to be using the radian measurement, which is pi over 2, to represent that. But we'll get there shortly. Now, I want to write these angles right here in terms of the inverse trigonometric functions. And this is how easy we could do that. If sine of x is equal to y, then x, which is what we have here, x is equal to the sine inverse of y, right? Because if sine of the angle is equal to y, right, then sine of y is equal to, the inverse sine of y is equal to the angle. So we could replace x here. I'm just going to draw an arrow out like that because I can't hold it, with sine inverse of y, right? Because sine inverse of whatever y is will give you that angle x right here, just like what we had. Up here, let's name this angle. Let's name this angle B, right? And we want to write angle B in terms of y and 1. So angle B here, if we're writing in terms of y and 1, it's going to be this side, it's its adjacent side. So therefore, the adjacent and this side is the hypotenuse. So it means that cosine of B is equal to y over 1. Because if you recall from high school, the cosine of alpha is equal to the adjacent over the hypotenuse. And that's what we just did right here. Cosine of B is equal to the adjacent over the hypotenuse, right? And that's just y over 1, which is just equal to y. And then we can get to the angle B by taking the cos inverse of both sides. So this is equal to cos inverse of whatever y is. And that gets you to the angle B. So I'm going to replace angle B with cosine inverse of y. And now let's go back to the interior angles of the triangle that we were talking about earlier. These must add to a total of 180 degrees, right? But we already know that this angle right here is 90 degrees. So it means that this angle plus this angle must sum to a total of 90 degrees. So we can write, I'm going to erase this piece right here. We can write this fact that sine inverse of y plus cosine inverse of y is equal to pi over 2. Remember I told you I'm going to use radians angles, right? So that's equal to pi over 2. That's 90 degrees. That's 90 degrees. This is in radians form, it's pi over 2. Now, if we know this, then it means that sine inverse of y is equal to pi over 2 minus the cosine inverse of y. All I did was to just subtract cosine inverse of y from both sides, right? Now, this right here, if we wanted to use x instead, we could, and I'm just going to do that because x is what I had here in the first place. So I'm just going to replace the y here with an x because we already have this fact. So it means that I can replace this here also with an x and an x. All right? Because this triangle was just to prove or show to you that this is true, right? So down here, if we look at what's here, sine inverse of x is equal to pi over 2 minus the cosine inverse of x, the sine inverse of x, right? So it means that if we take the derivative of this side of the equation, if we take d by dx of sine x, it's the same, it's going to be equal to the derivative of this side. It's going to be equal to d by dx of pi over 2 minus cosine inverse of x. So this right here is exactly the same as this right here. So if we found the derivative of this, it's equal to that. If we found the derivative of this, it's equal to this, right? So because of that fact, if we look at over this side here, and we take the derivative of the constant term right here, pi over 2 is a constant. The derivative of a constant is 0, right? And then the derivative, negative cosine inverse x is left. So therefore, the derivative, let's clean this up a bit. All right, let's not clean it up. Let's leave that and just This goes to 0. So what we're left with is the derivative d by dx of negative cosine inverse of x. I know you can see where we're going here. Now, this negative right here, this is actually a negative 1 being multiplied by the cos inverse of x. So we could take that outside of the derivative. And if we take that outside of the derivative, we will have sine d by dx of sine inverse x is equal to the negative of the derivative of the cosine inverse of x. And just to, because we're finished with this piece right here, let's remove this piece so we can take that up top, explain it a little bit clearer. So d by dx of sine inverse of x is equal to, remember we're going to take that negative out front, the negative of d by dx of cos inverse of x, right? And if we need to get rid of that 1, right, we could just divide both sides through by negative 1 to show that d by dx of cosine inverse x is just the negative of the derivative of the sine inverse of x. And this holds true for all the cofunctions. So if we find the derivative of tan inverse of x, cot inverse of x is just a negative of that. If we find the derivative of secant inverse of x, cosecant inverse of x is just a negative of this one. So in reality, what we're doing is just to find the derivative of sine inverse, tan inverse, and secant inverse of x. So let's go. Let's do that. All right. Now, starting with sine inverse of x, we're going to let y equal sine inverse of x. And then we're going to rearrange this here to say that sine of y is equal to x. So basically what we did was just to take the sine of both sides, right? So sine of sine inverse of x is just x. And then we have sine y on this side. So sine y is equal to x. So if we take the derivative of these two sides, right, we could get to what the derivative of sine inverse of x is. Let's go. And over here, we have implicit differentiation. So we have to find the derivative of sine y and take the derivative of y. So the derivative of sine y, if you recall, if you watch my previous video, you would see where I had proved this right here. The derivative of sine y is just cosine y. So the derivative of sine y is cosine y. And we need to take the derivative of y also. So that's just dy by dx. And that's equal to, the derivative of x is just equal to 1. Because if you look at the power rule, that's just x raised to the 1, right? So you subtract 1, you bring 1 down and subtract 1. That's going to be x to the 0. So you're just left with 1. All right? Nice. So it means that the dy by dx is equal to 1 over cos y. Now, we need to write the derivative in terms of x and not y. So we need to get this denominator of cos y in terms of x. Now we could use a triangle to do that, to save us from the trig identity. If we were going to use a trig identity, we would use the fact that sine squared x plus cos squared x is equal to 1. We would have used that. But I don't want to dive too much into the trig identities, right? I want to keep it simple, high school. So we're going to use a triangle. If we go to the triangle right here, a 90-degree triangle, if we know that sine of y is equal to x, remember, we talk about sine of y. So if this is angle y, the sine is equal to the opposite over the hypotenuse. So x, we could represent that as a fraction of denominator 1. So sine of y is equal to the opposite, which is x, over the hypotenuse, which is 1. So we established that. So we now need to find what cos of y is equal to. Cos of y is equal to the adjacent. This is the adjacent side right here. Let's use my favorite color. This is the adjacent side right here, this side. We can find that using Pythagoras' theorem, the fact that a squared plus b squared is equal to c squared, right? So we have c, a or b, doesn't matter what we name this one, and we could find this, and that's just going to be equal to the square root, right? It's going to be equal to the square root of this 1 squared minus the x squared, right? And to show you that that is true, if we make this, this is the hypotenuse, that's 1, so we have 1 squared out front is equal to b. That's just b, make x b, so that's x squared, plus this side is equal to a, we leave that as a squared. And we transpose right here to make or isolate the variable a. So a is just going to be equal to, we take that over that side, change sign. So that's 1 minus x squared. And remember that's square on the a right here. The inverse operation of squaring is square rooting. So we square root both sides, got the same thing. So that's what a equal to. So the adjacent side is just equal to square root of 1 minus x squared, right? So that saves us from using the trig identity, right? Now, cosine x is equal to the adjacent over the hypotenuse. The hypotenuse is 1. So it means that in reality, cos y, cosine y right here, the angle, is equal to the square root of 1 minus x squared, which is the adjacent side, over the hypotenuse, which is 1. So it's really just the square root of 1 minus x squared. So we can replace this right here. So we can further state that dy by dx is equal to 1 over the square root of 1 minus x squared. And we're finished proving the derivative of sine inverse x. So we can write that over this side. It's going to be 1 over the square root of 1 minus x squared. And again, because I've already shown you guys that this right here, cosine inverse of x, is just the negative of the sine inverse of x, right? So the derivative is going to be the negative of that, which is negative 1 over the square root of 1 minus x squared. Nice. So let's go to tan inverse of x. Still going to need that y, so let's move this over. All right. Coming together nicely. Now, tan inverse of x is what we are on at this time. So we're going to take care of these two in one working. Now, if y is equal to tan inverse of x, so we're letting y equal to this. Now, again, we take the tan of both sides, so that's tan y is equal to tan of tan inverse of x is just x, so that's just equal to x. And then we take the derivative of both sides, implicit differentiation again. The tangent of y, I didn't prove this one, but hopefully in future videos I will. The tan inverse, the differential of tan y, is sec squared y. So the differential of tan y is secant squared y. So that's secant squared y. And remember, we need to take the derivative of y also. So that's just dy by dx. So it's the inside outside function right there. And then that's going to be equal to 1, because the derivative of the variable is 1. Now dy by dx, because we're going to be dividing by sine square y, secant square y, on both sides. So that's equal to 1 over secant squared y. And again, we need to represent secant square y in terms of x. So to do that, the trigonometric identity would be really easier to use than the triangle, because the trig identity just gets straight to the point, right? So I think I'm going to use the trig identity here, because if we were using the triangle, we'd have to know that secant y is the same as 1 over cos y, and then we would have to go to cos y using the Pythagoras theorem and all around that. We could save us some time by knowing this fact right here, that secant squared y minus tan squared y is equal to 1. So it means that secant squared y is equal to 1 plus tan squared y, right? And tan squared y, we could represent that as tan y all squared. So the tangent of y all squared. So secant squared y is equal to 1 plus tangent of y all squared. And we know what the tangent of y is equal to. The tangent of y is equal to x. So all we have to do is to rewrite this secant squared y as, let's erase this right here. We could write secant squared y as, or let's write it in the next line, because we got space. So dy by dx is equal to 1 over 1 plus tan y, we have x, so that's just x squared. So for the tangent here, we have 1 over 1 plus x squared. And because I have showed you that the cotangent of that is just going to be the negative of that, let's just write that one right here. Let's draw an arrow because I think it's getting out of place. So it's negative 1 over 1 plus x squared. Nice. Now we're on to the final two. Let's go. All right. The final two. So we're on secant inverse of x. Same, we're going to let y equal to the secant inverse of x. And then we're going to take the secant of both sides. So secant of y is equal to x. And now, again, take the derivative, just the same. And again, we did not look at the derivative of secant y. Probably I'll do that with tan y in another video. But we know that the derivative of secant y is going to be secant y tan y. So the derivative of secant is going to be secant y tan y multiplied by each other. But then the outside, well, the inside function right here of y, we take the derivative by dy by dx, and that's equal to 1. Now again, we divide both sides by secant y tan y. So dy by dx is equal to 1 over secant y tan y. Now, of course, again, we need to get secant y tan y in terms of x, right? So it's nice that we have secant y is already just equal to x. That's great. But we need tangent of y, right? So to get to the tangent of y, the trig identity is the quickest route to this right here. So for me, at least, probably some of you could use a triangle or to get it just the same. But I think knowing this identity really helps. So we know that the secant squared y minus tan squared y is equal to 1, right? So if we know this, then secant squared y is equal to 1 plus tan squared y. And we need only tan y, right? I should be solving for tangent of y. Let's do that again. I'm solving for secant of y. I should be solving for tangent of y. So what I need to move is this piece right here. So tangent of y, and that's negative tangent square y is equal to 1 minus secant squared y. Yeah. And then we need the positive of that. So we need to remove that negative 1, right? So again, we just multiply the entire thing by negative 1. So tan squared y is going to be equal to secant, I'm going to put the positive out front, squared y minus 1, right? So tan y is just equal to the square root of secant squared y minus 1, right? Now we're on the right track. So we got tan y in terms of secant y because we know that secant y is just equal to x, right? So secant squared y, we can rewrite that as secant y all squared. So tangent y is equal to the square root of secant y all squared minus 1. Because secant y, we're just going to replace with x right there. So over here, on the other hand, we know that secant y is just x. So in reality, what we have is dy by dx is equal to 1 over x times tangent of y, which is the square root of, instead of secant y, I'm going to replace that with x right here. So that's just x squared minus 1. And this right here is the derivative of sine inverse of x. Now, we know that the cosecant is just going to be the negative of the secant inverse of x. So we're going to draw that arrow again down here. This one is equal to 1 over x and the square root of x squared minus 1. And then down here, this one is just going to be negative 1 over x times the square root of x squared minus 1. And this is all the derivative of the inverse trigonometric functions.